So jump, yeah, one of the which I can only think of running with more than 250 cores. I mean, that we maybe need to discuss that. Debugging MPI programs on large core counts is very tricky, for a whole bunch of reasons. And yeah, and it's the kind of thing we get in the query system. You know, I've got a program that it goes wrong, and it is difficult. We can maybe discuss that offline. There are, yeah, there's got a different approach, but it is tough. It is very tough to do. One nice thing that DDT does, though, one of the problems you have, I'm not going to delay the talk, but just very briefly, it's useful worth mentioning it. One of the problems you have in debugging MPI programs is you might have a variable which needs to be, it needs to be between 0.5 and 0.7, and you might print it out. And if you're running on 1,000 processes, it'll be really hard to see what's going on, because each process will print on process 95x is 0.7 on process 9. The good thing that DDT does is it will show you outliers. It will say, so it doesn't show you 512 separate windows or 512 values of x. It says, look, on most of the processes, x is here, but this one's weird. Or all the processes are at this line in the code except this one, which is over here. So they're quite good at presenting the outliers, and that's what you often want to find. And it's quite difficult to find that with print statements, but we can maybe discuss that separately. So this talk is called MPI optimization. It's a slightly, it's commercial. Distributed debugging is part of Forge. We have, but it's commercial, it costs money. We have a license on ARCHER2, but only up to 2,000 processes. I think it's not cheap. It's a very good tool, but it's not cheap. So, fine. So yeah, so I'm going to give Jeanette. Please ask questions in this, because I'm going to talk about various techniques and such like for optimization, but there's 101 things you could talk about here, but I'll hopefully give you some clues and some ideas. And we've got an example, which is, I said, it's a pre-packaged example, but hopefully reasonably useful. Right. So, I mean, just a very generic sense, you say your code isn't running well or isn't scaling well, and we get that now because, excuse me, software takes a long time to write. A lot of software we're running now was originally designed 20 years ago. There's nothing wrong with that, but the big difference is that machines have got an order of magnitude bigger. So a piece of software which was where the authors had a use case of maybe 1,000 CPUs on it, processes, is now running on tens or hundreds of thousands, and that's the problem. So at that high level, what are the things that can cause your program not to scale? Well, there's lack of parallelism, load and balance, synchronization, and communication. Lack of parallelism. Tasks may be idle because they're a subset of tasks computing. This is kind of obvious, I guess. It could be one task or several of them. Often it's tasks. Now, often in MPI programs, we designate task 0 as the controller process. There's nothing, you could designate task 93, but we pick 0. Unfortunately, the only cure is to redesign the algorithm to exploit more parallelism. The one case I would say here is that computers are getting faster and faster, but I/O is not keeping keeping pace. So what we do often see is people who have I/O problems now, because their I/O is sequential. They send all the data to rank 0. So if your I/O is a problem, then there's probably something you can do about it by exploiting more modern parallel I/O libraries, and we talk about those in a different course. But that would be something you could contact the help desk about. But okay, you need to redesign the algorithm. And the reason that the slides jump here is there used to be a bunch of slides showing how bad things could get, but I've kind of skipped over them. But Amdahl's law gives you a limit on your scalability, at least a broad brush sense. So if your code is only 50% parallel, your code can't go more than twice as fast on any machine. Well, ARCHER2, you could be running on hundreds of thousands of processes. So Amdahl's law would tell you that your code has to be, can't have more than 0.000% of serial code in it now. So it is very difficult to get programs to scale. Load imbalance is another one. All tasks have some work to do with some more than others. Now, load balance is very, if you're programming an OpenMP and a shared variables model, load balance, OpenMP has built-in directives methods for load balance. And the reason why it's easy in shared memory is you have a certain number of tasks to do. And at any point you can say, thread 0, could you do the first 10? Thread 1, do the next one. You can basically mix and match. Because there's a shared memory space, any thread can just grab any piece of data it needs. In message passing, if you want someone to process some data, you have to give them the data. So you have to say, well, I would like that process over there to do this calculation. Then you have to give them the data and possibly get it back. So actually, balancing the load can be as hard, it can be very expensive. You may require significant algorithmic changes to get right. And scaling to large process counts may be hard. Load balancing algorithms themselves may scale, they may take, scales of order P means they take, on 2,000 processes, they take twice as long as on 1,000. So, the load imbalance is very, very difficult to fix unless the algorithm was built in. Sorry, your method was built in from the start to take care of it. There are things you can do, and we'll see hybrid MPI+OpenMP can be a partial solution to that. But again, this is really an algorithmic thing. It's very difficult, and the reason why load imbalance becomes much more difficult on large numbers of processes is if most of your processes have 1,000 pieces of work to do and one has 1,010 or 1,100, you don't really care. That's a 10% difference. But once you scale up, the amount of work per process becomes smaller if you're doing strong scaling. And then you might have some processes with 10 units of work and some with 10 more. That's now 20. That's now twice as much. And so, again, that's a real problem. The one thing I would say about load imbalance is it can be quite hard to detect. So often people will run their program through a profiling tool, like, for example, Scholastica. And Scholastica will say, you're spending 50% of your time in all reduce. And then they'll come and say, all reduce is slow. No, if you're spending lots of time in collectives, the normal reason is load imbalance. In fact, although what's happening is that if one process is very slow, all the other processes are in the collective waiting for this slow process to turn up. So again, I haven't said that here, but a symptom of load imbalance can often be lots of time apparently spent in collectives. And that can be quite difficult to disentangle those two effects. So, I've got that here. Sorry. MPI program tools report the amount of time spent in each MPI routine. There on ARCHER2, we have the Cray specific ones, which is perf tools, but also we have Scholastica, which I think is quite nice. We had a course on that the other week. So for blocking routines, this time may result from it. So if your code spends a lot of time in collectives or a lot of time in receives, it could be because actually some of the processes are very slow because the task is blocked waiting for another task to enter the corresponding MPI call. So the other tasks are, now, tracing tools often show up load imbalance very clearly. However, tracing tools can be quite difficult to use at scale because they introduce their own overheads. But I would say lack of parallelism and load imbalance, unfortunately, on a few specific cases we might talk later, need to be addressed by the algorithm. Now, where you spend a lot of your time wasting time in a parallel program is synchronization. In MPI, most synchronization is coupled to communication. Okay, so that's what we're saying. In MPI, if two processes have to synchronize, then that's because of communication. And that can be blocking sends and receives. If I do an MPI S send and the receiver isn't waiting, then I wait for it to complete. If I do a blocking receive and the sender isn't ready, I wait. And also you might say you've used non-blocking communications, but even with non-blocking communications, you still at some point have to say, I'm going to wait for this non-blocking communication to receive, to complete. And collective communications are mostly synchronizing. So those are, it's waiting around for other processes that causes the delay. A very brief point, MPI barrier is almost never required for correctness. It's often used for timing. I mean, so, if you want to time a piece of code, You want all the processes to start at the same point. But it's very, very rare to see it. You can construct contrived codes where barriers are needed for correctness, but actually, to be honest, it's very, so people put them in. People are concerned. They say, put in a barrier before I call this collective operation. The way MPI is designed, if you issue a send before a receive, then the receive will wait. If you issue a receive before the send, sorry, if you issue a send before a receive, the send will wait. If you issue a receive before a send, the receive will wait. MPI is designed so that you do not need, almost never need, global synchronization for correctness. So 99% of the barriers you see in codes are not necessary, but they may be there for timing, for doing timing. The main point, though, is you may say, okay, David's told me that a load imbalance is a problem, but there, it isn't a problem in my code. All the processes are running at the same speed. Well, the point is they're often not. And this was discovered maybe about 20 years ago when people first started to build systems of more than 1,000 processors using shared memory computers. Just because your two processes are running the same code doesn't mean they run at the same speed. There's lots of random noise effects that can happen. For example, OS interrupts. Every now and again, the operating system wakes up and does a bit of I/O, maybe descheduling your process. The network may be contended, may be suffering contention. So two processes might communicate very quickly, and other two processes might be on a congested network connection, be very slow. So just because your algorithm is in principle doesn't suffer from load imbalance doesn't mean that it doesn't in practice. And so this has been known for quite a while. And unnecessary synchronization amplifies these random noise effects. If you have processes sometimes going faster or slower than other, the less of an issue it is. If you synchronize a lot, too much, that you're wasting a lot of time all the way through the execution of your program. Now, modern dedicated HPC systems like ARCHER2 will have the operating system tuned to minimize these things, but you can never get rid of it in practice. So let's think about, obviously, let's talk about communications. We'll talk about point-to-points and collectives, and talk about some standard patterns. So we've talked about this, but I've just written it a different way. Point-to-point communications typically incur a startup cost, which is the latency, which is the time for a 0-byte message, and then we can modify the total time for communications is the latency plus the number of bytes times the time per byte. But typically, we actually talk about this as a bandwidth. So this was our go-to model. The time for communication is the latency time, which we saw as a few microseconds, plus the number of bytes divided by the bandwidth, which is hopefully in the many gigabytes per second. As I've said before, it's faster to send one long message versus many small ones, but that's an easy. But it's also better to do an all reduce of 2 doubles rather than 2 all reduces of 1 double, because again, if you do an all reduce, 90 whatever % of the time in the all reduce is the coordination of the processes sending the messages. If the message is 1 double versus 2 double, well, they'll take exactly the same. Remember, the protocol message is probably 128 bytes. So in fact, so although it's replacing 2 sends of 1 byte with 1 send, 2 sends of 1 integer with 1 send of 2 is quite easy. You should think about it for your reduction operations. And you might say, well, I can't do that because I have to reduce an integer and a double at the same time. Well, derived data types can be used to do this. You can basically do a reduction on a derived data type, which is a combination of a double. So there are techniques to do these things. So you should think about this a small number of large messages rather than a large number of small messages applying to collectives, such as all reduce, as well as to the more obvious point-to-point. So various communication patterns can lead to additional synchronization or delays, which can show up as a slow-performing program. And we can have, this is then to our design. Communication patterns is how processes talk to each other. And there's certain terminologies which people use, a number of patterns which can be the cause of poor performance. Now, you could identify these by hand, but actually the Scholastica tool, which I mentioned there, not only will measure the time spent in different routines, but will also attempt to characterize them. So if you're lucky, the Scholastica tool it's very flexible and therefore can be quite difficult, not difficult to use. You have to try a bit, but it can say, I think it looks like this. The reason for the slow performance of this program was caused by one of these issues. It won't just say it spent a lot of time in receive. It will say you had a late receiver, which is what I'm gonna. So there are certain patterns which people characterize, and some tools like Scholastica are designed to try and highlight these to you, the user. So late sender. If a blocking receive is posted before the matching send, then the receiving task must wait until the data is sent. And this is obviously most critical. So this is time going left to right. If you post a receive before the send is ready, you wait, and then the sender sends the data and the transfer happens here, but you've had a lot of waiting time. So if a blocking receive is posted before matching send, then the receiving task must wait until the data is sent. That's called late sender. You could call it early receiver, but it's called a late sender pattern, okay, where you're waiting for data to come in. Out of order receives is similar, but what might happen is this process is looking to receive data from this process and this process, but this process is sending first, but you issue the receive to this process first. Therefore, although this guy wasn't late, unfortunately, you weren't able to receive from the sender because you issued the receive to this send first. And so if you could swap them round, then you could reduce the overall time because you're receiving the messages in the right order. So out of order receives is sort of similar to late sender, but it's caused by the receiver receiving the data in the wrong order. Now, if you have a completely deterministic program where this process is always faster than this one, then you can solve this by saying, well, clearly, if I know this process is the faster one, I will always receive from this one than that one, as in this pattern here. But as I said, in practice, the reason that this sender is after this one is probably due to random fluctuations, okay? On this particular iteration, this guy got descheduled, or I don't know, sent a message down a very slow link and was delayed. So it's although your delays may be caused by out of order receives, often you don't know what the order should be because it's random. And that's where you should use non-blocking communications. We'll talk about this a bit. You should not prescribe an order for things. Okay, you should try and be able to tolerant to a more general case. And the solution to that is to use techniques such as non-blocking communication, which I'll mention later on. Late receiver is obviously the sort of flip side of late sender. If send is synchronous, the data can't be sent unless the receive is posted. Now, the send can be synchronous for two reasons. Either you call MPI+ send, or you may call MPI send, but with a very large a large buffer size, in which case MPI is not able to isn't able to do the trick of using the ego protocol. It resorts to being synchronous. So again, it's the inverse of late sender. The send is waiting for the receive. So I've mentioned this before, but I'll reiterate it. MPI progression, you probably think of MPI as running continuously. And so if you have asynchronous or non-blocking communications, you think they're happening in the background. Okay, you tell MPI to do something, you come back later and it says it's done it. Your mental model is that it was kind of doing that in the background while you went along. And that would mean that communications and calculation can overlap in time. This is not generally true. Again, we'll talk tomorrow about ways you can improve overlap of communications and calculation. But as I mentioned before, the MPI library is generally single-threaded. So communication can only be processed when your program calls an MPI function. As I mentioned, I've actually talked about this in advance. MPI treats these calls as manual interrupts. in some sense. And again, I said it before, in a modern, if MPI were designed today, this would probably not be the case, but it is true. So if you issue a non-blocking send, okay, you're saying, please deliver this message, and I'll check later whether it's arrived or not. If there's an existing receive, it could be sent immediately because there's a matching receive and it goes in there. If not, what you imagine is it kind of trickles along in the background, but it probably can't be sent until the next explicit MPI call, okay? Because what you'll have done is you'll have sent a protocol message to the receiver. And so until the receiver calls an MPI call, it won't see that. Or you've said to MPI, please send this data. You then return to your main program. Your process may get a message saying, actually, I'm ready to receive, but that can't be acted on until you next call the MPI library. And this can give strange effects. So what we've got here is late progress. What happens is you have issued, time's going left or right. This process has issued a non-blocking send to this receiver, okay? But the receiver isn't available, isn't ready to receive it yet, and we're assuming here that we're not doing so it's not ready to receive it, and so the copy is made in some internal buffer, okay? And then it returns. So I'll come back to that, Cameron. It's a good question. What happens is this is the one that yes. So what happens is that the sender is delayed until the MPI library is re-entered by the sender. So for example, what I'm saying here, you've issued a non-blocking send here. This guy wasn't ready, okay? So nothing happens. This guy issues the receive, but your process here is running some other non-MPI code. Later on, this code could call a receive, but the first thing the receive does is, before it even does the receive, it says, oh, wait, is there anything stuff outstanding? And it notices there's an outstanding I send, and therefore it completes it, okay? So the sender is delayed until the MPI is re-entered by the sender, and in this case, the re-entry is actually a receive. So in this case, a receive issued by me, this process, triggers the sending of the message which was sent way back here. And so that, that can be quite hard to spot and can cause issues. So late program extra large MPI sends and profiling. Yes, so I would have said the normal reason for extra large MPI wait times is due to load imbalance. That would be the normal reason, that basically you do an MPI wait, and hopefully at that point there's a bunch of messages to be, say the waits are for receives, for example. There might be maybe somebody is really slow and they haven't got there yet. So it could be, but it could also just be good old-fashioned load imbalance. It's a good question, though. I think that one of the difficulties in MPI is it's quite hard. It's often a moot point as to where you attribute the time. So for example, I could put some timing routines around an ore reduce, okay, and that might show an awful lot of time spent in the ore reduce because there's some of the processes are slow. But I could then put a barrier before, and the time would show in the barrier, but then the ore reduce would be quick because everyone would enter it at the same time. So I think even for profilers, there's some ambiguity about where they actually allocate the time. Do you see what I mean? But I would say, Karen, it's very good. I would say in principle, yes, but in practice, my first port of call would be load imbalance for that. I don't know if that was useful. But... So the way to basically get around all this is if you have a situation like this, okay. The reason you have this situation is that you insist on receiving a message from this process before that one. And this is the standard communications pattern. If you're doing halo swapping in 3 dimensions, you have 6 of these going on, up, down, left, right, in all 3 dimensions, and possibly even more. So the trick is not to impose an ordering, okay, when there doesn't need to be one. And non-blocking communications is a way of doing that. So as I said, you can avoid explicit late sender receivers by more careful ordering, but often the time delays are actually caused by random noise effects, network congestion, or OS interrupts. Not all tasks take the same time to do the same computation. Not all messages are the same length, take the same time to arrive. So I would say the right way to do communications, and we'll see this as hopefully the winning example in my benchmark we're going to run at the end of this, is to use all non-blocking communications entirely. So do all the sends, all the receives as non-blocking, and then end them all with a single wait all. Because if you actually, sometimes people do lots of non-blocking copies and have lots of individual wait alls. Well, again, that's just, if you have an individual wait, you should never wait on it. If there's more than one communication to go on, you should wait. So here is that if you did non-blocking communications here, yeah, you'd issue the send and the receive, and you call a wait all here, say, and then MPI would just be able to say, oh, who's ready? Okay, this guy. MPI can see all the messages. It can deal with the messages which are already there while the other ones are coming in. So I think the most elegant way to program, and the way that's most tolerant to random noise causing load imbalance, is to program with all non-blocking communications. That's lots of I sends and I receives. Use a single wait all to complete it, and if you can, thinking about how it was post all the I receives as early as possible. Again, that means, so that can be quite challenging to do, but that would be, if there was one sort of, take home message, it's this. A lot of people use send receive. I should have a slide on that here, apologies. The problem with so one of the problems with MPI is if you just use send and receive, MPI send and MPI receive, you have the danger of deadlock, okay? Because you can't be sending and receiving at the same time. So send receive, a single send receive is a way of breaking that deadlock, but it only breaks it pairwise. So often people will do halo swapping with 6 send receives, okay? Send receive up, send receive down. So that is still imposing an ordering. When you do the send receive up, you're waiting for the up process to be ready. Well, maybe the left process is already there. So I don't like, although send receive can break the deadlock in most cases, I think it's a bit of a dead end. And when I teach the MPI course at the introductory level, I mention send receive, but I discourage people from using it. And if you look inside an open source MPI library, send receive will be nothing more non-blocking send, non-blocking receive, and wait. I mean, there's no magic to it, right? I think you should program up yourself. So this is normal halo swapping, okay? So I've got to give some background here that we've got a standard situation, maybe an example like this. You have a 2D array, okay? This is your array here. So you're operating a 1, 2, 3, 4, a 6x6 array. And that has some update scheme, which here involves its 4 nearest neighbors. So to update a data element, ij requires information from I minus 1, I plus 1, j minus 1, and j plus 1. This is a local thing. We don't need to bother about that. And so we can identify of our 6x6 array in our parallel program 3 regions. One is this core region, where the computation can be done independent of other processes because all the data is local. We have this boundary region where the computation cannot be done independently of other processes because if I'm here, j plus 1 is there, okay? And then what we do, the classic trick, is to extend this with halos, so the arrays are not of size m by n, but m plus 2 by n plus 2. I've got this m by m here. And so what we do is we do a two-phase thing. We do a halo swap. We bring in all the boundary data from the other processes. And then having done that, we can update the entire region because we know all the data. So that's the classic communication calculation. Swap the 4 halos, do the calculation. Then we have to re-swap the halos. The point is, if you order these halo swaps saying, right, I'll wait for the message coming in from the top here first, well, that's maybe a stupid thing to do because maybe this guy down here was ready first. And so do not impose unnecessary ordering of messages. Okay, don't say loop over the sources, receive the value from a particular source and then loop. Don't say receive. Don't go. I'll communicate with the guy up, the guy down, the guy left, the guy right. Okay. So wait any is a so I'll come back to that. So in this situation, okay, in this situation I cannot proceed. This is I've got a two-phase thing. I do the halo swaps, then I do the calculation. The way I've drawn it here, I cannot do the calculation until all the halo swaps are completed. And so you want to, so there's you can use wait any in a case in which there's stuff you can do as you go along. I'll come back to that. Here, wait all is we cannot do this calculation here until we've completed all the 4 halo swaps. So you should do this with a wait all. But there are cases where you could benefit, at least try to benefit from wait any. I think I know what you're getting at. So what you should do in principle is loop over source and receive the value from any source and end the loop. And now the loop just counts the correct number of messages. Okay. However, I would avoid well, it's a bit difficult. It's hard to do this with wildcards for various reasons. So what I would do is, to implement this, issue separate non-blocking receive for each source, and then issue a single wait all. Okay. You don't want to impose unnecessary ordering. Okay. What some people do is they loop over directions. They send up, receive down, maybe with the send, receive, and send down and receive up. Okay. What you want to do is loop over directions and then do all the I send up, I receive down, I send down, I receive up, and then wait on all the requests. So that's what I'm saying. I've got a few too many slides here. What I'm saying is here, issue all the send and receives. This is only for a 1D case, but equivalently for if you had left and right, and wait on all the requests. Now, what you can try and do now is you can now try and overlap communication with the calculation. Because what you can say is, well, this diagram says swap the halos, then do the entire calculation. What we could try and do is start swapping the halos while the halos are going on in the background, because we have a non-blocking comms. We can update this core region because this doesn't depend on the halos in this simple 5-point stencil case, and then we wait for the halos to complete, and then we can complete the updates for for the boundary region here. So you have 3 regions. This is the data which can be updated independently of the other processes. This is the data which cannot be updated independently, and it's also the data you have to send and receive. And this is where that data is received on your peers. So what you can do is you can say, well, what we'll do is we'll start the non-blocking send and receives. We will now loop core region, which is 2 to n minus 1, 2 to n. I realize I made a typo here, but anyway, just then we do this update. Now, in reality, this will be like 1,000 by 1,000. Or in reality, the amount of computation in this region will dominate that. Then what I've got here is wait for completion of all the non-blocking sends and receives, and then complete the calculation of the 4 edges. What you could do with Cameron's suggestion is you could do 4 ways. You could basically say, right, I've completed this calculation here. I need to wait for the halos to update this data. So I try to update this data. Rather than waiting for all the halos to come in, I could see which one comes in first and then process that. So you could do wait any. Oh, this guy's come in, I can now update these. Is that kind of what you meant, Cameron? It's only if you've got other stuff to do, but you can't. I have seen people do that. In practice, this will introduce extra code complexity, which actually can kind of kill you in the end. Yeah. So okay, fine. So I've had this. Okay. So I've got a naive example here where the incoming data is just copied. But yes, I can't remember. I can't remember who it was, but I had the same conversation where I was talking at cross purposes, but then I've discovered, like you, there's a lot of processing with what's received, but it is a mess. And what I would say is if you program up something complicated, please, 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 please retain the simple one, because on some platforms the simple one will be quicker. So always maintain the simple version for two reasons. A, it's your reference file, it's your reference implementation, which is less likely to have bugs in it. So you can say, if you've got some really complicated overlapping communication calculation, processing the incoming data on demand, it's quite easy to make a mistake. So you need to have a version which does something much more simply as a reference. But secondly, that simple version can sometimes be quicker, bizarrely. You can do persistent communications. So instead of this, I receive, I send, I've covered this before. We do persistent com set at once. And I have actually mentioned this already. But this course has been pulled together from a larger course. And so there was some repetition in places because of the way the lectures are ordered. Neighbor collectives are, what I'm saying here is, don't tell MPI what order to process the data in. Just tell it what you want to do and let it sort it out. We've done that in this case by issuing all our individual sends and receives at once, and then tell MPI, wait for it all to finish, and you just match them up as and when they come in. Neighborhood collectors are actually a single call which allow you to do this all at once. We'll cover this in the next lecture. So but they can, the reason I mention them here is they can be used for halo swapping. So standard collectors apply to whole communicator. MPI all gather collects data from all P processes, all of them. And neighborhood collective applies to your neighboring processes. So MPI neighbor, the American spelling, all gather only collects data from your neighbors. Who are your neighbors? Well, it requires your communicator to have a structure, a topology, and I'll review briefly what they are next. But when you put MPI processes into a Cartesian or graph topology, you say who their neighbors are. So in a Cartesian topology, your neighbors will be up, down, left, right, your six nearest. It interprets these are the six nearest neighbors. So in a regular grid, you've got a Cartesian topology via MPI can't create. And in the 3D grid, an MPI all gather would gather from the six nearest neighbors up, down, left, right, forward, backward. And in fact, it may not be obvious, but MPI all neighbor all to all allows you to do halo swapping in a single call. So what you're telling MPI, this is exactly what I want to do, and MPI can then implement that in the most efficient way. So you're encoding all the communications you want to do in a single call. MPI all to all, MPI neighbor all to all. Now, in practice, we'll see in the benchmark that this is almost exactly the same performance as doing this, because I suspect the neighbor collectors are still relatively new. I suspect people have just implemented them in this way, but they're still there. They're still there. So, sorry, for halo swapping, the MPI implements halo swapping, and in the halo bench exercise, which is what we do immediately after this, then I have done that. In practice, you need to play around with data types to get this to work. I'll explain that later, but at least the benchmark illustrates the concept. MPI can implement it any way it chooses, hopefully efficiently, but your code is more elegant, hopefully. Again, so we can discuss that after the next lecture. I won't label these. There are some similar synchronization point patterns for collective comms. They're a bit more obvious. Late broadcaster. If you have a root process who broadcasts data to other processes, if the root process is late, then all tasks have to wait. And it applies to other ones which have a root, which is, and actually you often see this because often your code is if rank equals 0, read data from file and then broadcast. So everybody else enters the broadcast first, but you rank 0 are reading from file here. And then now often there may not be any way of solving that actually, but you often see a lot of times spent in broadcast because of late broadcast. But often it's just a symptom, a side effect of doing I/O on a single root process. Early reduce again. If you have a reduction which isn't an all reduce, which is just a reduce where the answer is only placed on a single process, that could be slow if the root process calls it early. And the more common one is weighted end to end. Okay, so if we have a collective routine which requires the active participation and synchronization of all processes, And the classic ones are all reduce, which we do all the time, and all-to-all or all-to-all-V, which are used in often in parallel FFTs for global transposition of data. And so basically, you can't do the all-to-all, at least until everyone has entered. And so if somebody enters early, the other people all wait. Again, often the symptom of load imbalance. That is a classic, applies to all-to-all and all-reduce are the ones which you'll see in practice, I'm sure. The collective communicators are hopefully well optimized. It's very rare that you need to implement them point to point, but they're expensive because, I mean, the point of parallel programming is to make your code go faster. So you hope if you run on 2,000 processes, your code goes faster than 1,000. But it all reduces slower on 2,000 processes than 1,000 because it has to do more communications. Now, hopefully, it's only a bit slower, but it is still slower. So, you know, collective scale. Even if you have a good collective, it will take longer on more processes. So it's helpful to reduce their use as far as possible. One way is to aggregate, do an all reduce of two reals rather than another. If you have a convergence, if you have an iterative method where you check for convergence, sometimes it's better to reduce the frequency. I mean, you know, it might be more efficient to check for convergence every 10 iterations rather than check for convergence every iteration. Now, that might mean you do 9 extra iterations, but if you're doing 1 million iterations, what's 9 between friends? So that's a trick you can use. There are non-blocking collectors around in MPI+3 where you can say, please start doing this reduction operation or this all reduce, and I'll come back later when I want the answer. In practice, for a whole bunch of reasons, I've never found them that useful. They tend not to be particularly well implemented. Also, in many algorithms, unfortunately, you need the reduction. You need the result of the reduction operation immediately. There's often no lag. You know, you've computed some input data and you need to reduce it. You need to use it the next. If you think about things like conjugate gradient, if you ever programmed them up, you have dot products, and immediately next you some scalar parameters. The dot products of 2 large vectors, and you need to use that scalar parameter almost immediately. So people get very excited about the non-blocking collectives. I'm not. Maybe I'm old-fashioned, but as in many things in MPI, it's often a loop that they introduce a new feature. People tend not to. People try it out and it's not very efficient, so they don't use it. So it languishes. Then once people start using it more, they complain and they fix it. That was very true of MPI+. MPI+, was introduced way back. A lot of people tried it and it was really not that efficient. So people stopped using it. But then when modern machines, maybe 15 years ago, got much bigger, people were forced to use MPI+. They went back and said, look, your MPI+, doesn't work very well, and then it was fixed. So maybe it's just, it's one of these circular things, but I've not found them useful, but I haven't looked at them for quite a while. So general advice, try to avoid imposing any non-essential message ordering when messages are actually sent. When messages are actually sent can change on every run. Try to allow MPI to deal with messages as they happen. Issue all send and receives as non-blocking. Issue receive as early as possible. Complete with a single wait all, unless, as we have a situation where Cameron mentioned, where you can, there's a lot of processing done when you might want to do lots of wait any's. Set them up with persistent comms, be careful about message ordering, or use neighborhood collectives, and avoid unnecessary collector calls easy by aggregation. And I keep saying one of my bugbears, do you really need all those barriers? So summary, we've done these 4 patterns, okay? So the exercise, I mean, it doesn't, one of the problems about the advanced courses is it's very difficult to come up with a programming exercise which is useful and doable in a constrained amount of time. When you're teaching basic MPI, Hello World, and things that are, you know, they're worth writing. So this next exercise is, again, there's no programming, but it's a benchmark. And so if there are no questions, I was just basically going to spend 5 minutes going through the exercise, which we'll do until 3:30. But I don't, if people have any questions on that, on those topics. Fine. Okay. So if you do this, yeah. Whoops, sorry. This code is correct because I've ordered the I receive and I sends such that send to the down process is guaranteed first to receive, which is that one. However, the whole point about persistent communications is you give as much freedom to MPI as possible. And so when I do that start all, although MPI knows it has to start these 4 functions, it's allowed to start them in any order. And so you can get bugs where you get the wrong sends and receives, the wrong sends and receives. So what I have to do is when I do these receives, I don't know if you know, every message can have a tag. So I would tag these 1, 2, 1, 2, 1, 2. I would have to tag them. Yeah. So the problem comes if you're up and your down neighbor are the same, and you're thinking about simple halo swapping example. You've got 2 messages coming in. You have to make sure they go to the correct halos, not the wrong way around. But you could tag the messages for the up halo with 1 and tag the message with down halo with 2. Does that make sense? So you need extra. Sorry, maybe if a tag isn't. Oops. Oh, sorry. I'm just being an idiot here. Maybe. Yeah. So just to be clear. So if I do. Yeah, it's just this tag man MPI send. When you do an MPI send, you specify a tag, and the send tag must match the receive tag. So, for example, you would need to have if you were sending tags in a 3D halo swapping, you'd have tag 1 for the up message, tag 2 for the down, 3, 4, 5, 6. I normally don't use tags. I normally just set the tags to 0 or something, but this is a case where you might need them. I don't know if that explains it. I may not interpret your question very well, sorry. You have to make sure that the up send and the down receive have the same tag. So I can write. So while we're here, we can go on to the, am I still sharing that? I am, okay. So the exercise is, it's detailed on the, I've set this up as a, I will share the right screen, and that'll make things easier. So, okay, so the exercise here is actually the 3D halo swapping benchmark here. So there's a README there. So, so all this, I mean, you can just compile and run it, but all it does is it basically sets up a 3D array of processes, swaps halo data up and down in all 3 directions. And it uses 1, 2, 3, 4, 5, 6, 7, 8 ways of doing it, every way I could think of. So first of all, it does pairwise in turn using send receive. Okay. So the problem is you can't do send, receive, because in general you'll get deadlock. But you can do send receive up, send receive down, send receive left, send receive right. That works, but I don't think it's particularly efficient. You can do a trick, which some of you may use before, to do sends and receives, but break the deadlock by doing a checkerboard or red-black, as I call it, coloring of your processes. So if you think about it, especially with nearest neighbor comms, if half the process, you split the process into 2 groups, and the odd processes send first and receive second, and the even processes receive first and send second. So you basically pair them up. That's a technique people used to use. Then we do pairwise swapping in each dimension, but using I send, receive, and wait. Pairwise swapping each turn using I receive, send, and wait. Pairwise swapping each dimension is using I receive, I send, and wait all. And then the ones which I think should be the best, non-blocking covers all directions at once using I receive, I send, wait all, and count equals 12, because we have to complete a send and a receive in each of the 6 directions. Sorry, we have to do a send and a receive, a factor of 2, For up and down, another factor in all 3 dimensions, so 2 by 2 and 2 to 3 is 12. Persistent communications, which is very similar, and I have a neighborhood collective there, which won't make sense at the moment, but will make sense after the next lecture. So I apologize that for historical reasons this is written. Sorry, not apologize. I shouldn't. But for historical reasons, this is written in Fortran, and so that may not suit most of you. But hopefully, so we just do. Actually, I'm now sharing the wrong window. So we just do git clone this thing here, and it goes there. Okay, we go to cd Halo bench. You should really edit the ARCHER2.job so that it does what were the 2 those things in it. So QS equals reservation. No, I've taken too many out there. This is running on 8 nodes. You can do it on more, but 8 is at least you have 2. Oh, I can't even spell partition. At least with 8 processes, you probably have a 2 by 2 by 2 grid. So at least there's real communications in every dimension. Yeah, that just does that. And if I look at the code, well, I can do what have we got? Is it make -f make file ARCHER2, hopefully. So this is Fortran. There are some warning messages. The modern compiler is very touchy about Fortran modules for reasons I don't quite understand. But the code is correct. I don't like having the warnings, but I don't quite understand that. But if you look at the code, again, this is Fortran, but hopefully reasonably well written Fortran, at least by my standards. So n buff is 10,000. That means the halos are of size 10,000, which is 8. They're double precision, about 80k halos. Oh, where do I say Q sub? Is that in the instructions? Did I say Q? Sorry, I've not. Yeah, sorry. Q sub is when. Sorry, way back we used to have PBS. Where have I? Yes. Okay, fine. It's S back. Yes, correct. I will fix that immediately. So thanks. That's a hangover. Sorry, from when I used to run this. Our systems used to use PBS, not slow. Thanks for spotting that. I'll fix that. We have. Yes, we're just sending data up and down in the 6 dimensions, and all I do is I have these 8 tests, which you can look up what they are on the web page, what they are, and then I basically have I create my Cartesian topology, so I arrange my processes into a 3D grid. And that will probably for 8 do them a 2 by 2 by 2 grid. I think it prints out what that is, and then basically it just loops over all these calls and calls halo send receive, halo red black, which requires an even number of processes, and then we call halo I send 6 strange names. So if I maybe look at the one which I think is going to be the best, which is halo I receive I send wait all. Hopefully, again, halo swap.f90, I think it's called. This is it here. Yeah. I mean, I'm not saying it's particularly understandable, but hope it's fairly explicit. I loop over, sorry, That's up, down. That's the dimension. Sorry, that's not up. That's is it send or a receive? That's over the dimensions 1, 2, 3. That's over up, down. And then if it's I call an I receive or I call an I send. It's just this is doing all 12 in a one. It looks complicated. It's not. It's not complicated at all. It's just bookkeeping. But then the main point is we do a wait all of all of them. So the code's hopefully fairly explicit. But I think the main thing is just to run it and see what exam answers you get, and we can sort of discuss the. There's not a huge amount, unfortunately, not a huge amount to play around. Well, no, the various things you can do. So I will submit this. It might be interesting to vary the buffer size. That'd be an interesting thing to do. I'll basically have if I do. So just to check, I've not made. Has somebody managed to? I think it's a 5-minute break to get another glass of water. I didn't want to leave if people were having. So there was that issue with. There was that. Yeah. So I'll fix that issue that you spotted. Thanks with. Good. Right. So back to. So hopefully I've fixed. Yeah, S batch now. So I would think it would be also be to do. I would maybe change the buff size to be very small. That could have a big effect because 10. So these halos are 10,000. They're probably big, I don't know. It depends what you're. But I would maybe or very large, bigger the eagle. We saw the eagle might have to be an order of magnitude more, or even bigger. Yeah, an order of magnitude more. But you will or run on different numbers of nodes. You can run on up to 24 nodes in the current reservation, but you will need to note that you will need to change the number of recent runtimes. It doesn't self-adjust, and so again, just to show you how to do that, even if you're not a Fortran programmer, it should be fairly straightforward to where's Eleanor one to fix that. So you'll need to recompile. But if I wanted to do, okay, so nbuff is the size of each halo, so the buffers are, that means 80,000 bytes, and this is the number of repetitions. So if I wanted to say nbuff equals 100 and bump this up by another factor of 1,000, I would have to do that and just do make. No, make file ARCHER2, sorry. I don't want to recompile. So those are the things to maybe play around with, and I'll go back so they're actually on the screen. If you're interested in Halo, okay, we can. This is for but there. I'll leave these. There we go. So I'll maybe take a 5-minute break. Well, I'll be back. So please carry on, but I'll be back live here in just in 5 minutes, just so we can discuss the results. I just need to take a slight break just to clear my throat. It's fine, but I'm getting again sort of brownouts on this long compile time isn't a long compile time. It's I/O on the work file system. That's the normal reason. So it's a bit unfortunate. Okay. Did anyone have any? I could look at these numbers. Did anyone have any clear conclusions as to which was the fastest, or are there any obvious? I can look at the. This is the default configuration, 8 nodes. Oh, that's interesting. Okay, I've not. Okay, that is interesting. Okay, so that's interesting. So with the default configuration, the send receive, which is what a lot of people do, is okay. Okay. So send receive is not brilliant. Okay, 500 megabytes a second. Red black, which pairs them up, is a bit tricky to do, but surprisingly good. Don't quite understand why. The pairwise I send I receive wait is a bit less again. So all of these impose an ordering. All of these are looping in some sense over dimensions and directions at once. Send receive, red black, yeah. I receive, I send actually all of these are doing that. The pairwise one, again, so all these are very, very similar. This is the one which I think, yeah, there we are. So this all non-blocking. So this does, all these do exactly the same amount of communications. This issues the same calls. This one here and this one here issue the same calls. It's just that this waits every pair and this waits once at the end. And I think that shows you what this impact of not, the only difference between this and this is that this doesn't impose an ordering. This one doesn't. And you can see it's a really significant 30% improvement. The persistent and neighborhoods are, I always find this being very much of a muchness. The neighborhood is so close to this, I suspect the neighborhood collective issue would just literally be that code that I've written, to be honest. So these are just so close together that I don't. Oh, sorry. My idiocy. Apologies. Thank you. LN01. Sorry, I hadn't. So go back to the start to recap sort of saying which you couldn't see. Obviously, apologies for that. Yeah. So this is the default configuration. The send receive, which is what a lot of people do, really doesn't get very good. It's 500 megabytes a second. The red black is surprisingly fast. This is the complicated matching up sends and receives. Whether you do non-blocking send and receive or non-blocking receive and send is not much of a muchness. So the very important difference between these two calls here is that these issue exactly the same send and receive calls. It's just that this one waits for every pair to complete. This one waits at the end for all 12 to complete. And you can see that, so the only difference between these two is at what point you relax the synchronization here compared to here. And you see that you get a 50% increase in bandwidth, or maybe 30%. And persistent neighborhood and this are all very similar to each other, suspiciously similar. This one I reduced the buffer size significantly and just guessed. Okay, that seemed to work. So this is basically only 100. It's very small amounts of data, And I'm seeing a similar pattern here, that send receive is the worst. That I send and I receive wait all is very good, better than these guys by again. That is about 50% better, if not more. And I saw, okay, again, these may have some noise in them, but 0.1 seconds not that much. But yeah, it's and then the other ones I did, the last one I did was back to the default parameters, I think, and back to the default parameters, but on the biggest, well, on yeah, oh, sorry, I'm on more processes, and someone spotted the bandwidth does drop. I mean, I guess that I guess that's just more network contention. I guess you're just well, actually, what did we do here? We just ran on more processes. Yeah, it's there may be more off-node communications going on here. And another, also, it's very important to realize that this is a saturation test. This is you might be surprised that these numbers are in the hundreds of megabytes per second, not the tens of gigabytes per second. But remember, on a PC system, you have one or two network interfaces coming off a node. The node has 128 CPU cores on ARCHER2. So with the ping pong, a single CPU core has access to the entirety of the network. But in a real program, all CPU cores are communicating at the same time, and therefore the network is shared between them. And so what you could do, for example, on this, is I could just do, I could send the same amount of data between nodes. I'm always very nerve-wracking doing things live. But what I could do is I could send, okay, I could send 128 times as much data from each process, but I could have one task per node. So what I'm doing here is I'm basically saying I'm swapping halos, but each same amount of data, but each process has exclusive access to the network. So let's see what that does. So I am running. Let's hope it's running correctly. Okay, so here you're getting back to, because this is more like a ping pong. So previously each process was getting, say, 500 megabytes, but remember, to get the bandwidth on and off a node, you'd have to multiply that by how many processes were communicating between nodes, and that would be lots. But here I've done almost more like a ping pong test. So we should get, and we're getting this 10 gigabytes per second, which is what we got for the ping pong test. So that is consistent. It's taking about, it's going to take quite a while, but if I look at that, is it 2, 4, 3, 4, 3, 8, 6, 4, 6, 3. We're getting, yeah, we're getting the same back. So you may have wondered why the bandwidth there was so much down on the ping pong. That's because there were lots of processors sharing the network. Here you're much more, and there's not really a lot of difference between all this. So here you're just saturating the network completely. So there's the synchronization issues look very, very, yeah, they're almost identical here. It's interesting. So okay, so hopefully this is interesting. But I think you know the clear message is, if we look at this guy, which was quite the first one I ran, that don't do lots of send receives. Not a good thing to do. You should use non-blocking, but you should do as much as non-blocking as possible, and that means I send, I receive, wait all, and then we get really good. The persistence are quite good. Neighborhood collectors are all much or muchness, but all these three methods have all the communications ongoing at the same time and let MPI sort it out, and you can see quite a significant benefit in performance there. So I'll take a break now and come back at 1600 for